Thank you very much. It's a pleasure to be here, and I would like to thank the organizers, wherever they are, for organizing such a wonderful workshop, and also to all of you who are still here. All right, so I guess I'll dive straight into it. And in the spirit of one of the previous talk, I'll start with the what and then the why. All right, so random states. Well, what are random states? Well, I'll be talking about either random pure states. So, which I guess I'll denote as usually by a cat, which is going to live in some Hilbert space and of some dimension. So for example, say if I were to choose a random state, I'm going to impose that it's going to be normalized. So a random pure state is just a state that is, there's a more technical way of saying it, but a uniform distribution among the Hilbert space of a certain dimension. Or I could be talking about random mixed states, where like a density matrix, where I think of it as a operator in a Hilbert space, such that the trace of rho is equals to 1. Here it's going to be more ambiguous what I mean by a random density matrix, because there are various measures that you can reasonably kind of call random. So I'll return to this point, but okay, so this is first general idea. Okay, random state, but okay, before we get too far into the that aspects, the natural question is, well, why random states? You can see this, right? In the dark. All right, so there are various reasons that you might run into a random state. Probably from a quantum information perspective, they tend to be, in some sense, the distributions could be a fixed point for most time evolutions, right? So this is something we're not going to talk about, but if you throw something into a black hole, people rave about thermalization and how it becomes random. The reason why I'm going to look at random states is because there are cases where we just have limited information about the system. So if you want to make a prediction when you have limited information, well, you just pick a random state and see what you get. Maybe it becomes close to what you have. Of course, this naturally leads to the next question, which is, when is a random state a good proxy for a generic state for of whatever problem you're interested in? Right, when is it good for your problem? So as an example, if we're studying ground states of, say, generic local Hamiltonian, we know random states are typically very bad at that because of the area law, whereas random states follow the volume law. In contrast, if you are studying, say, a random eigenstate of a non-localized Hamiltonian, then a random state turns out to be pretty good, actually, description at what you're going to find. So one of the things is that specifically is we're going to ask in what cases do you get good results by taking a random pure state or a random mixed state on the system. Right, so I'll get more specific about what I'm addressing over time, But before that, I would like to switch a little bit and talk about the various things that various entanglement measures that I want to analyze on these random states. So I'm going to switch a bit about like what I mean by random states and the various entanglement measures. Okay, so the first one that almost everything is built out of is the entanglement entropy. Which I assume most of you are familiar with. So I'll just write down the definition. S of rho is equals to minus the von Neumann definition. There is also the Rényi definition, which I'll denote as sub alpha. Which in some sense is a generalization of the von Neumann entropy. And this one is important. Oh yeah, thank you. This one is useful because it tends to be generically more easily computable using something like the replica trick. This one has much better behaved properties. So one of the tricks, as I will talk about a little bit, is that sometimes you calculate S alpha, and then through some magic extrapolation, you send alpha to 1, where you get the von Neumann entropy. Right, so that is one measure. And already, based on this, we can talk about the bipartite entanglement of a pure state. So whenever I say that, the picture I have in mind is that there's AB, there's a pure state on AB, and I'm interested in either so psi in AB, and I'm interested in S of rho A, which in this case is the same as S of rho B. So that's what I meant. All right, so moving on, there's also mutual information. And in this case, it will be a mutual information of a mixed state. And the definition is equals to S of So mutual information in some sense measures how A and B are correlated. The two main properties that we will need are, and I'm saying this just for the sake of completeness, that is always positive. So that's additivity of entropy, and that the mutual information vanishes if and only if the density matrix factors into a product. Okay. So, all right, so these are various, these are standard. All right, so the next one I'll talk about is what's called the reflected entropy. It's a little bit of like a niche quantity, but I'll kind of explain certain properties of it and why I'm interested in it. It's called reflected entropy, and credited to Dudley and Faulkner for coming up with it. All right, so the construction is as follows. It is defined for basically a mixed states on two party, AB. All right, so first thing is what we need is we need a purification of the density matrix. Specifically, we're interested in a purification of rho AB. And the definition for purification is that it is any wave function that lives on a larger Hilbert space, AB plus some ancillary auxiliary space, such that if you trace out the auxiliary space, you get rho AB. So this is just a definition for what purification is. So every density matrix emits at least one purifications, and there's an infinite number of them for every density matrices. We're going to work with what's called the canonical purification, which operationally, if you're someone who just does numerics, we're going to basically take the square root of the density matrix as the purification. So, of course, in order to dig this comparison, you square the wave function and, right, but more accurately, the canonical purification is defined this way. So suppose that I have a density matrix, which is an operator on the Hilbert space. The canonical purification of rho lives in H times H star. So it's the same dimensionality in terms of the number of numbers you need to put it on a computer. But I think of it as a wave function instead of an operator. And if I do an eigen decomposition of rho, so these are orthogonal, then the canonical purification of rho is written as basically take all the eigenvalues, take the square root, and then it'll be phi I tensor phi I. And then to make it canonical, we think of the second space as like some conjugate of the first space. And so what happens is to check this identity, you square this and trace out the auxiliary space. And so you just get phi, and then this gets squared. All right, so that's called a canonical purification. So in particular, in order to define the reflected entropy, what you do first is you first take the canonical you take the your density matrix and you take the canonical purification. Pardon? All right, so if I'm going to formally define canonical purification, I'm going to have to start with the Hilbert space and H star. And H star, like, you can think of it as a dual space of H, if you will. Or you can also think of a conjugate. Yeah, so the way you go from ket to bra is you take all the coefficients and you complex conjugate them. This is a little bit of abusive notation, I have to admit. Yeah. Like numerically, what I'll do is I basically like take the matrix and then take the square root and just flatten it, and that's what it is. So that's what it is if I were to write code to do it. Formally, what happens is this kind of a structure where you think of the auxiliary space as a mirror of the original space. Like, there's a conjugate of it. So every wave function that lives in H, there's kind of a corresponding wave function that lives in H star, but there's a conjugate on it, like all the coefficients gets complex conjugated. Well, when I make this construction, implicitly, I'm also going to have a map from H to H star, which is like an anti-unitary map. It's not too important for what we're gonna, like the details, this particular detail isn't going to be that important for what I'm going to be talking about. All right, so I take the purification of a density matrix on AB, which means I make a copy of the Hilbert space. So I call those A bar and B bar. So I now have a pure wave function that lives on A bar, B bar, AB, A bar, B bar. And the reflect entropy is defined as of A colon B of this state is defined as basically the entropy of half the system, AA bar or equivalently BB bar of this state. I will talk about entropy of purification in a second. This is like the poor man's of doing it. Yes, that's my next topic. All right, so the way I think about a picture is that, okay, so if this is my system, density matrix, then my purification is going to be a pure state on something that's twice as big. The Hilbert space is square as big, actually. And then what I'm doing is I'm basically taking a cut this way. And the reflect entropy measure is this. Uh-huh. Yep, you get the same entropy. Yep. What this does is that this is like, I just write it this way because technically this is not a unique decomposition. Like you can add phases to it, but like this is written in a way that the canonical purification is, at least once you define this Hilbert space, is unique. This is just a technical, like, and for this part of the talk, completely unimportant. Well, if it helps, there is an isomorphism from the, that's a bra, right? The bra of phi to the ket star of phi I. Yes. Yes. I would be very happy to talk about this later. But at least for this measure, none of these tiny things are important. Yes. The quantum what? Quantum double? I don't believe so. I don't believe so. There is sometimes a name for it. Like if rho happens to be like a thermal matrix, like E to the minus beta H, then this is sometimes called a thermal field double. And people in holography love this. Is like, black hole, white hole on the other side, blah, blah, blah. That's their picture of it. Here, I'm literally just taking the square root. I'm thinking of a setting where this is just an arbitrary state. Yeah. You can also do it. Like if you think of like, I'm just saying, just think of yes. Okay, but anyway, all right, so this thing was defined, okay, but I'm going to start listing some of its properties. And this is where I also don't need this. Okay, Okay, so all right, so what is its properties? All right, so the first property is that this quantity is bigger than or equals to the mutual information. The proof of this just follows from strong subadditivity of Voigt-Neumann entropy. So, and it's also given in this paper, but it's like a 5-line proof by basically using the strong subadditivity over and over again. It's also upper bounded by 2s of A and also 2s of B. That one, the way I see that one is basically, well, okay, so we're interested in an entropy of AA bar. Now, keep in mind that because this is a purification of this, if I take this system and I only look at the density matrix on A, I'm going to get rho A back. And A bar will be its mirror image, so basically also rho A bar back. So the entanglement entropy of AA bar must be less than the entanglement entropy of A and A bar together. And if the mutual information is 0, which means that it's a product state, then the reflected entropy is also 0. Because it's a product state. If it's a product state, then you take the purification of A and B individually. And so AA bar is a pure state, BB bar is a pure state. There's no entanglement between them. But because of this band, where the mutual information is bigger than I, this arrow goes both ways. All right, so this is a somewhat, right now, artificial quantity that I've defined. There's actually one more relation. I'm just going to write it out and explain it like a bit later. For if the mutual information is less than a half, then there's an alternative upper bound, but this is less than or equals to minus I log I, where I here is the mutual information, minus 1 minus I log 1 minus I plus I all right, so this is an expression I'll come back to. This is basically an upper bound on the reflected entropy based on I, where dA and dB are the dimensionality of A space and B space. Right now, I guess the only thing that's important is that as I goes to 0, so does the reflected entropy. And it turns out it's a continuous quantity. So when I is small, in some sense, this tells you what's the largest possible growth of this reflected entropy. And the term that we're going to focus most on is this, which is a term that depends on the dimensionality of the space at a later point. And all right, so questions. It is kind of completely, it's not very motivated right now, but I'm going to talk about entanglement of purification in a bit, which motivates this. Okay. Okay, so it is an entanglement measure. Well, yes. And so does the reflected entropy is also like mutual information, and that it does also classical correlation quantum entanglement. So here, yes, strictly speaking, it's not like this quarter squashed entanglement. Okay, so let me talk about entanglement purification. All right, so the entanglement purification and this will be like of a state. The entanglement purification is equals to the minimization over all purification of AB where I minimize SAC of this wave function. All right, so the picture is, again, I have a density matrix that lives on AB. You can think of all the possible purifications that I can write down that lives in A, B, C, D. So think of all the possible purification, and basically the entanglement of purification is the entropy of whatever that the minimum possible entropy once you kind of consider all purifications. So minimize basically the Bipartite entanglement of this pure state. And this is called entanglement purification. All right, so the first property that all right, so the first property is that the entanglement of purification is always going to be less than or equals to the reflected entropy. And this is by definition, because the reflected entropy is the entropy for one specific purification, and this is overall possible, is minimized over all possible purification. It is also lower bounded by mutual information, or specifically, it's lower bounded by half of the mutual information. Which means that the entanglement purification is, if the entanglement purification is 0, that implies that the mutual information is also 0, and that is only possible when you have a product state. This again follows from strong subadditivity. Now, one of the reasons why the entanglement purification comes up is that it's often one of the measures when you do disentangling operations. So, for example, uses. So, for example, if you say have a matrix product state, sometimes what you do is you apply, say, a unitary on 2 sites, and what you would like to do is you would like to find a unitary that minimizes this entanglement. And so in this particular case, I can think of these 2 sites as A, this is C, this is D, and these sites as B. So the way you can think about applying a unitary is that I can think of that I'm optimizing over purifications of a certain Hilbert space dimension, and I'm trying to minimize the entanglement between AC and BD. And in this sense, this gives you a lower bound for the best that you can do. So theoretically, this quantity captures how efficient certain disentangling can be. And of course, the disentangling also shows up in certain things like, for example, the mirror, where one of the ways, it's not the way, but one of the ways you can construct a mirror is basically starting from a wave function is basically by finding a bunch of disentanglers shown here in X, and then doing decimations, and then repeating. So this quantity basically reflects how effective it is. And it also shows up in certain things. For example, in the isopeps, the Moses move has a disentangling step in it that also does something like this. All right, so right, and that gets to the point. The entanglement purification is notoriously difficult to calculate. Basically, as far as I know, the best algorithm is that you start with a guess and you do some gradient descent or some version of optimization on it. And you hope that you've got a good one, because there's also no easy way to check that you've got the minima. Typically, the landscape of purifications has a lot of local minima, so it's very hard to know that you've got the global minima. So this is actually a notoriously difficult quantity to calculate, and I hope I'm still correct. I think it's still unknown whether it's additive or not. That's yeah, so that's basically like how difficult this quantity is in some sense. The dimension? I believe there is a result. I think it's something like the square of A and B on each side, I think. It's like an upper bound. There is an upper bound for like what's the largest C and D that you have to search to guarantee you find a minimum. That result does exist, but I don't have it at the top of my head. Numerically, of course, you don't usually fix the system size C and D, so numerically you might also not even be able to hit the minima if your Hilbert space is too small. All right, so what do we know about EP? Well, EP is difficult to compute. But on the other hand, the reflected entropy is easy to compute, because there is just linear algebra. So there's this conjecture, also by Duller and Faulkner. The conjecture is that the reflected entropy is monotonic. Specifically, the conjecture says that S of AC BD is bigger than or equals to S of AB, SR. But if this conjecture is true, then this conjecture implies that the entanglement of purification is bigger than or equals to half of the reflected entropy. So over here, we have an upper bound for the entanglement of purification by the virtue that this is just a purification. Here we have something far non-trivial, which is a possible lower bound if this conjecture was true. Doesn't have to be ACBD, it could be AXBY. So if you imagine that I have a density matrix on full poly system AXBY, but I'm thinking of AX as kind of the left side and BY as the right side. So this is a density. So I'm going to start with a density on AXBY. If you trace out X and Y, I'm going to get a density matrix on rho AB, and which I can do this calculation. So by virtue of basically tracing out pieces, you can still define the reflected entropy, and the conjecture, monotonicity conjecture, is that it decreases under tracing out. I can also do it this way, because it's symmetric, the definition, yes. Wait, sorry, say that again. Which one, X? Yeah, so in here, it doesn't, yeah, it's not part of A or B. But in the definition of reflected entropy, you do have to kind of say what's on one side, what's on the other side, and what's on neither of those two sides. There is a partial transpose in there, because what you do is you first take the square root to get the canonical purification, and then you, I think of a full-leg tensor, and then you, or you can think of it like a block matrices, and you do a partial transpose to basically put AA bar on one side and BB bar on the other side. So numerically, the way I'll program this is that I'll take the square root, I'll basically like turn into full like tensor, and then I'll switch two of the tensors, combine them again, and take the entropy of that tensor. Oh, it's not, sorry, it's nothing to do with partial transpose, sorry, my bad. Yes, yes, okay. But that's how basically like, that's programmed on the computer. Okay, so this is the conjecture, which gives a lower band for EP, which is much tighter than the mutual information. And the point I want to make, and it's taken me a while, the point I want to make is that the reason why we look at reflected entropy is because it's easy to calculate, and if the conjecture is true, it basically provides both an upper and lower band, which is basically the tightest in some sense that at least I know of the entanglement purification, which is often a quantity of interest in many algorithms. And so in some sense, I'm going to use the reflect entropy as a proxy for the generic behavior for the entanglement purification. What happens numerically is that like one of the algorithms we do is that we start with the canonical purification, and we try to lower the entropy by doing some, say, conjugate gradient descent. And it could be because the algorithm don't perform very well, but most of the time we end up with entanglement purification very close to the reflect entropy. But that could just be a feature of like poor algorithm design. Oh, some holography stuff. Yeah, I'm not going to talk about that. Yeah, it was like holography and all that things. In fact, in holography, that actually becomes like an equality, I believe. Yes. So if you mean like if AB is a product, if a product. Uh-huh. Uh-huh. Okay, so if CD is just a product state, okay, so this has to be a pure state. Okay, so are you saying if AC is a product with BD? Yep. What if all the phi i's were product states? I mean, it's still possible for your orthogonal basis to be a product state, like in say classical, like information, but there will still be entanglement. I'll have to work on an example for like what you're asking because I don't think I have an answer on the spot, but I assume the answer is not trivial. Okay. Okay, so, all right, so now the main question that I actually want to ask, or I guess like the first question I want to ask is as follows. Given a pure state on some system ACB, so think of it this way. And you can think of this as a 1D chain, if you will, if it helps you. The question is, if I'm allowed to basically apply an arbitrary unitary onto space C, what is the generic entanglement purification or the generic reflected entropy of this state? So what generically will you get? So what is EP or SR of this? And we can also ask what's the spectrum, though I won't get to that answer to that question in this particular talk. And of course, again, EP is hard, SR is easy, and I'm going to focus mostly on basically the reflected entropy. So if I take some system where I don't know too much information, what is just generically the reflected entropy, and therefore basically asks the question, how hard is it to disentangle the two sides generically? And I'll also show applications to 1D chains, where you can imagine this is literally a chain and left, middle, right. All right, so that's kind of the driving question for what I want to talk about. All right, so for this, I'm going to have to kind of work up with random states what the entanglement is, what bipartite entanglement is, the mutual information, and what the reflected entropy is. For the sake of time, I'm mostly going to just skip the results. There is actually a calculation in here, but I'm running out of time. All right, so the first thing is bipartite entanglement entropy of random pure states, which is to say that suppose I take a random state psi in the Hilbert space HA times HB. I'm basically, my definition of random is that the measure is invariant under all unitaries living in AB space. So that uniquely defines what it means to have a random space. Or basically one way to think about it is that I'm going to choose matrix elements where A runs from 1 to the dimension of A, B runs from the dimension of B, such that it's normalized. All right, so this problem has actually been worked out, what the entropy of A and B is. So I'll just skip ahead and literally just write down the answer. There's a tensor network calculation here to actually do this in the theme of this conference, but for the sake of brevity, I'm just going to skip all the tensor network stuff. Okay, so the result, and this is due to Page, Don Page. The expected entanglement entropy of A and also B is equals to log dA minus dA over 2 dB when when dA is less than or equals to dB and is equals to the mirror expression when dB is less than or equals to dA. So what I'm showing here is basically like a large D expansion. So when both D's are much bigger than 1, the entanglement entropy, bipartite entanglement entropy of a random state is basically given by, I'm going to assume A is less than B, the log dA minus some quantity. I'm going to make a plot of what that is. And this is a plot as a function of log of dB for fixed dA. And the plot looks something like this. This is the average entanglement entropy. The dotted line basically illustrates what the theoretical maximum can be from subadditivity. So, or even simpler than that. The entanglement entropy between A, B can't exceed the log of the dimension of either side. And that's what the dotted line represents. And this shows basically the average is very close to the maximum. In fact, for all intensive purposes, unless this lines up to here, unless the two dimensions are similar, basically it's always just a log of whichever one is bigger. So if I ignore this, if I only look at the first term, it's just the log of whichever one's smaller. Which is intuitively, that kind of makes sense. Entropy kind of measures, at least in statistical mechanics, the number of such states. So generically speaking, you're going to expect the largest possible entropy if you sample uniformly a whole space. All right, so this is the result. So very roughly, we can write that the expected S is equals to the minimum, the log of the minimum of dA dB. Pardon? Yeah, there's a minus 1/2 in here, yep. The maximum is log A, but not every state is at log A. So there's a tail in the number of states with lower entanglement entropy, and when you do the average, you get basically minus 1/2. Right. So it's basically the maximum that you can possibly get, but because it's an average, it has to be slightly less than that. Okay. Oh, I'm not going to be able to pull that back down. Huh? Oh, that's that for that, okay. Okay, so that is for random two-body pure states. So now, how do we do a random two-body mixed state? So there's not really a canonical way to sample over mixed states because the condition that is invariant under all unitaries isn't strong enough to constrain what all the possible density matrices are. So for the purpose of what I call random two-party mixed states, what I'm going to do is I'm going to consider a free-party pure state, and I'm going to trace out one of them. We'll consider a random free-party pure state called ABC. And I'm just going to let rho AB be trace over C of this wave function. And the Hilbert space dimension of C, in some sense, going to control what the distribution of rho AB is within that space. In particular, I'm going to assume that we're always in a regime where DC is much bigger than DA and DB individually, which is much bigger than 1. So you do this construction, find a pure state, trace out C, and that gives you some distribution of density matrices. which I'm going to explain to you what it looks like. All right, so if you do this, what's going to happen is that generically, the expectation value of rho A is just going to be proportional to identity. And this is because if I look at A, the other two space B and C together is so much larger than A that you're just going to expect the maximally mixed state. Similarly, the expectation value of rho B is going to be 1 over dB. However, the expectation value of rho AB is going to depend on the size of C relative to AB. So this is the way this is set up. Yes? Is this, I think this is normalized. Average of the density matrix under this ensemble. But I should also mention, actually, this is the average, but I should also mention when I actually do this, the spread is also tiny. So for intensive purposes, I can pretty much get rid of the average and say that even if you pick a random state out of this, you're going to get something close to 1 plus something that's very, very, very small. That for purpose of this discussion is 0. So it's more than just saying the average is this. It's basically saying that the typical sample is also exactly this. On the other hand, rho AB will not be exactly the product based on what C is. All right, so I'll just kind of give the result for the calculation. On the horizontal axis is log of dimension of C. And the key marker here is log of dimension of A times dimension of B. So the behavior is going to depend on whether C is bigger than AB product or less than AB product. And the curve basically looks like this. The mutual information is going to look something like this. It's going to be very small when C is much bigger than AB. And when the C is less than AB, this is going to be a linear increase on the log scale. And just for reference, this is going to be a half. So this is the average mutual information. One way you can think about why this is the behavior, or at least the way I think about it, is that I think about, okay, so I think about a free body state on ABC, where C is, I'm comparing C to the product AB in terms of size. So when C is much bigger than AB, then almost all the entanglement A is between with C and almost all the entanglement of B is within C. So as C goes to infinity, A and B are basically have no entanglement between them. And that's why the mutual information decreases. And as C drops below the product AB, the entropy tells you that the entropy of AB can no longer be just the sum of SA and SB because of the balance of entropy, and that's when mutual information starts developing. Now, we'll be mostly interested in the tail. Right. I can also plot the reflected entropy, which is another tensor network calculation. And it basically looks something like that. That goes up really quickly. I'll write the expression in a minute. So SR is bigger than I, as we have established earlier. And again, in this limit is where it's a product state, so they both go to 0. Right around here, this is on the order of a log dA square, or dB square, whichever is smaller. So while this is on order 1, the reflected entropy around here is on the log of Hilbert space dimension. I realized that since I'm the last person here to give a Blackboard talk, this advice won't be very useful. But don't clean the front board before the backboard because the water drips on you. Pardon? Okay. No, I'm gonna make sure they all get wet, man. If I have to suffer. Right, so so the expression is as follows. To leading order, the mutual information is going to equals to dA dB over 2 dC. Or at least that's the leading order when dC is much bigger than dA dB. So this is basically, again, it decreases with the dimension of C. The reflected entropy is equals to minus K log K minus 1 minus K log 1 minus K plus K minimum log minimum of dA square dB square, where K is, it's to lowest order I over 2, but then there's like extra terms after that. So K is some complicated function, but to leading order is like half of the mutual information. So this is basically the result. Basically, you, again, take a random free body state, pure free body state, trace out C, go through this entire procedure, and we kind of get this. And we've kind of seen an almost identical expression earlier. If I'm going to write this in terms of I, this is roughly minus I over 2 log I over 2 plus I over 2 plus I log minimum of dA dB. And just for consistency, I'll divide by 2 here and square the argument. Very similar to the expression I wrote earlier, except it's I over 2 instead of just I. And there's also over 2 here. All right, so again, as I goes to 0, which is what happens when you send C to infinity, this expression also goes to 0. But this expression goes to 0 much slower than I. So there's, of course, this term, which shows up on the order of log I, but there's also this term, which depends on the dimensionality of the two spaces. And I guess the message here is that even when mutual information is small, which is one measure for correlation between a system A and B, it is still possible for both the reflected entropy and therefore, assuming the conjecture is true, the entanglement of purification could be very large. So this is basically a statement saying that if you actually want to do a disentangling, you can have two states that have low mutual information, but yet still have quite high entanglement of purification. They're related, but it's mostly this factor that could make them very different. And the other thing I want to point out is that this expression isn't close to the theoretical band. So earlier, the theoretical band basically didn't have the over 2s, whereas the expression for the expected entanglement entropy is almost to the theoretical band, like minus order 1 constant quantity. Okay, so this is basically the result when I take random states. Now, why do we care about any of this stuff? Let's go back to the motivation for a problem again. And the first observation that you are probably going to think about, again, is that most interesting states are not random. Or at least random in the way that we've defined it so far. If anything, you've probably spent a lot of time programming a computer to generate non-random numbers. All right, so, right, in particular, so far for everything I've talked about, say the density matrix is equals to 1. And usually this is not true, right? Usually, you're going to be interested in states where it's not proportional to the identity. Right? This is kind of a boring state when you try to measure anything out of it. And so, what I'm going to do is I'm going to change the question. All right, 15 minutes in. Okay, so the actual question that I'm going to change to is, okay, so consider a random pure state in random pure state, free body ABC again, but such that we restrict what the density matrices are on both the A space and the B space. So I'm going to, such that is trace on both A and B is fixed as part of the distribution. Then the question is, well, what are or is the SR of this problem? And we can also ask, what's the spectrum? So before that, we just basically had what I would call an unrestricted pure state, and we can crank through the calculation and basically calculate, say, well, this is how hard it is to disentangle it. Well, okay, but we don't usually have random states. So let's say I have a random state with the density matrix on A and B are known. So I fix that, and among that space, I sample randomly, and then ask, so I really have to define, okay, so I'm still gonna pick a star of a random distribution. Okay, so the way that I define a distribution is that I'll define like the weight of a particular state. If it's just unrestricted, I'll basically write the delta function of the norm minus 1. So this is what I call the unrestricted. I'm just gonna sample over all states of norm 1. This is not a group, so it's not hard, but it's in spirit the same as a Hall random distribution, in the sense that any unitary, it's a distribution on size, so that any unitaries on it, it also gives the same distribution. You're shaking your head, it's okay. This is the Kronecker delta function. So I'm basically sampling states. If this is like the weight of states, and with this condition, that yeah. So before these two distributions, this one by itself can be written this way. No? This is basically okay. So the first condition is basically say it's actually redundant from the second one. The first one basically say I'm only looking at states whose norm is 1. Yep. That's equivalent to that, yep. You can also think of just pick one random state, apply a Hall random unitary to it. Yep. The other two conditions, the way I think about, okay, you really don't like this, okay. Okay, and then I can add in additional conditions, which is saying that I'm going to impose that trace over BC. So the subdensity matrix A is matches this. So it will now be the distribution is now a function of this, and also a function of this. So of all the random states I have, I'm going to choose the subset that satisfy these two. Okay, so numerically, that would be extremely inefficient because this is a measure zero subset. So, but inefficiency aside, one way I can implement this is basically generate a random unitary, apply it to my state, and then just have it within epsilon of this, like element-wise. And if it's not within epsilon element-wise of this, I throw it away. And then if it's not of this, I throw it away. So that's inefficient, but that will give me that distribution. Now, typically, this is going to be like an exponentially small subset. So very inefficient, but that's at least the spirit. There is a numerical way of sampling this that my student has implemented, and it doesn't obviously work that way, but okay? Yeah. Okay. All right, so this is the actual question, is that, well, suppose I actually know rho A and rho B, and really the only thing important is the eigenvalues of A and eigenvalues of B, right? So basically saying I know the Schmidt spectrum of A and B, how hard is it to disentangle the system? All right, so how much time do I have? Oh, all right. I'm going to write down what the procedure is. To actually solve this. And I'm not going to explain why it works or whether it doesn't work. All right, so here's the procedure. And it seems completely ad hoc. I'm going to pick a system A, B, okay, I'm going to pick an alternative system, A prime, B prime, C prime, such that the Hilbert space size, let A, dA prime, dB prime, and dC prime be such that when I calculate, say, the expected entropy of A prime, the expected entropy of B prime, and the mutual information of A prime, B prime. So I'm going to choose these three spaces and pick random pure states inside the space with no restriction, such that when I calculate these three quantities, this equals to S of rho A, this equals to S of rho B, and this equals to I of AB. So I'm just going to pick these three numbers, and usually they end up being irrational, so that when I plug into the formula that, I get the quantity that I actually want, specifically the entropy of rho A, entropy of rho B, and whatever the mutual information is. And then what I claim is that with this system, A prime, B prime, C prime, I'm going to compute the average reflected entropy using that formula. And somehow, this will be very close to the actual answer to this question that I want. The new system is completely random, and I'm changing the Hilbert space dimension for this new system. And I'm choosing a new system to match the specific observables of this. Pardon? Yeah. Yes, that's erased, yes. So I'm going to choose dA, dB, dC so that those lines, wherever they are, matches with these quantities that I want. Yeah, so I should really rephrase this question. I'm also going to choose a random, really, okay, so really the way I should phrase the question is I'm going to choose a random density matrix, rho AB, such that these two are true and the mutual information is some fixed value. Right, yeah, so density matrix is way harder to define and measure, and I do have a rigorous definition for it, but for the purpose of this conversation, I'm going to skip that definition. So, and so given these three quantities, this is an approximate algorithm that gives you what the actual reflected entropy is. All right, since I'm out of time, I'm going to show some data. All right, so this is data. All right, so this is data from my student. He basically did exact diagonalization on the Ising model. And it's 13 sites long, A is 6 sites long, C is 1 site long, and B is 6 sites long. So remember the geometry is ACB. And basically, the red and green curve of the left is the only thing you have to look at. So these are like nodes that are sent. So ignore everything else besides the left two plots. And it's the red and the green curve that you should compare. One of them, the green curve, the labeling is also very poor. The green curve is the reflected entropy calculated from the wave function of the ground state. And the red curve is the reflected entropy calculated using this method, where you basically try to find a random parameters that fit the stuff. And so I guess the main feature is that the red curve and the green curve matches. The horizontal axis is like the transverse field in this transverse Ising field model. Okay, we also did it for the small Ising model. We also did it for the XXZ model. And again, it's the red curve and the green curve that you should be looking at. The green curve, again, is the numerically calculated reflected entropy, and the red one is the analytical one by fitting the parameters. All right, so there's actually a reason why this works, but since I have like -3 minutes left, that reason's going to have to wait. All right, so that's kind of my main result. Thank you very much for your attention. And I would also again like to thank the organizers for inviting me here. Yep. Statistically speaking, they will be about the same. So the idea of this is that suppose you only know rho A and rho B, but or like the entanglement spectrum of two different cuts differently, but say mutual information and also the mutual information between them, it basically gives you an approximate estimate for what the entanglement of purification and also the reflected entropy for the system is without actually doing that calculation. Now, you might think that calculation is trivial, so like, why would you do it? But you should think of this as a proxy for entanglement of purification, which is difficult to do. Oh, yeah, so, right. So in these plots where I say A, B, and C, so I close it down, those are the physical length of the 1D chain. And so when I take a random state, the bigger C is, the lower the mutual information A and B is. And that is also true physically. The more sites C have, the lower the mutual information. But now, since like the transverse field Ising model is a relatively low entanglement state, you don't need many sites of C in order to achieve this low entanglement limit. So Oh. Short answer is I don't think so, but I didn't check. All right, so thank you very much.